We did look at this form of getting our differential form of dG into delta G. We have free energy of the products minus free energy of the reactants, remembering that Gibbs free energy is a state. Okay, it's a state function. You can calculate G for a given state. So here's an example of Gibbs free energy for a chemical reaction, a super popular one. You've seen it in other classes. You're going to see it a million times more. All right. It is ATP plus water being broken down into ADP and a phosphate ion. Okay. Remember, we already talked about how oversimplified this equation is, right? It's not even balanced on both sides. Like where is water over here? And it's often drawn like this. This is all that ever needs to be shown, typically, in other classes. We're not showing any non-covalent interactions that are happening with water. We're not talking about any interactions with an enzyme facilitating this. This equation by itself, like written as this chemical reaction, doesn't necessarily show us anything about entropy, right? I mean, that reaction, just as it's written, is missing a lot of information. And we know a lot more goes into it, but what's important is delta G. It wraps up some delta H and some delta S that isn't shown by the reaction itself, all right? But delta G will be roughly negative 30 kilojoules for every mole I break down of ATP. Okay. This is the standard state free energy change for the hydrolysis of ATP. Okay, standard state's going to be denoted with this naught, okay, this superscripted naught here. Okay, it's negative because this reaction releases energy. The negative sign indicates the reaction proceeds to the right spontaneously, okay? So this direction is the spontaneous direction. And if I flip this arrow, or I want to flip these two so that I'm still reading it to the right, the sign of this is going to flip, okay? This becomes a positive. This means that free energy of ATP in water, the reactants, okay, are obviously higher than ADP and the phosphate ion, the products, to make sure that products minus reactants becomes a negative value. And here's just sort of a generic graphic of that. They haven't drawn maybe some initial input or anything here, but we're seeing that we're going from a higher free energy of our reactants to a lower free energy of our products. Okay, take a look at the units. It's negative 30 kilojoules per mole of ATP that's broken down. If I wanted to get the free energy change of breaking down one molecule of ATP, what do? I'm going to divide by Avogadro's number, right? We think in moles because it's a tangible quantity we can think of, and we don't have to have these like absurdly little, times 10 to the negative 23rd joules on everything, all right? This is also for 1 mole, right? If I break down 2 moles of ATP, it is going to be negative 60 kilojoules, and I'm not going to put per mole on the bottom because that is no longer correct. It is per 2 moles. So mind your units, okay? I don't care if you don't put per mole on the bottom. If you've made only 1, that's fine. It's per 1 mole. Definitely don't put per mole on the bottom when you aren't making 1 mole of something, okay? If you're making 2 or 3 or 4 and you just write per mole, that's wrong. And so here is a website to try for to mole or not to mole, how to decide what units you use, whether it's right or not, okay? This has been an issue in the past few semesters of how to decide whether you can leave it on or not. So I recommend